Hello and welcome to a new video. This is for Precalculus using the Math You See curriculum. We're on lesson 19, which is about functions, relations, domain, and range. Now I'm going to be honest, most of what we've done thus far, if not all of it, is what I would consider trigonometry, which is a part of many Precalculus courses. But we have really not been doing much algebra. And that's the other part of Precalculus, is reviewing algebra skills and building algebra skills. And so this is really going to take us back into the realm of algebra. So for some of us, this is probably going to be exciting. And we're not completely leaving trig behind yet, but typically people can be split up into two categories really, really easily, right? That's always how this works. So some people like algebra better, some people like geometry better. You may or may not feel like trigonometry is similar to geometry. The point being that maybe this will be a nice change for you, that we're kind of going back into the realm of algebra. So that's my hope, at least. So let's take a look at some vocabulary. Okay, so just about anything we talk about in math is a relation. What we do is we relate things to each other. So the most common way we do that is that we relate x's and y's together. And typically we do that with an equation, with a set of points, with a graph. Each of those is relating two values because whenever you have an x, you put a y that goes with it. So either literally you've got a set of points and so you can see the x and y's, or in an equation, you could pick what x you want to plug in and you get a y out. Or on a graph, you could look for where the points are on the graph, that like, okay, if x is 5, then on my graph it's 8. So all of those things are relating x's and y's, or whatever letters we want to use. We're relating things together. So we basically take a set of inputs and then we end up with a set of outputs some way. Sometimes we just make them up. Like if I just make up a set of points, I've probably made up the relation. If I have a graph or an equation, well, I may still have made them up, but there are rules that govern the way the inputs and the outputs work, that you can pick whatever you want typically for the input. But with an equation or graph, right, they behave a certain way, so they give you a certain output. So whenever we get into the realm of especially equations and graphs, then there's a set of relations that we especially like in math called functions. So a function is a specific type of relation where each input has exactly one output. And so what that means is if you are curious about the input 2, if it's a function, you know that the input 2 has exactly one output. It doesn't have more than one. If you input 2 into an equation, you're not going to get multiple answers for that if it's a function. So that's nice, right? Like it actually seems weird, right, to think if I put something in, I'd get more than one thing out. But there are actually equations and graphs and relations that that happens with. As we're talking about inputs and outputs, there's another set of math words that we use to describe those. The set of inputs we call the domain, and the set of outputs we call the range. So I'll fill those in here. Domain and range. And this is something that this is kind of the way we do math, and you know, we've been doing it like this for a while. We typically use x and y, right, for our equations, for our graphs and things like that. So when you're doing this, domain or inputs also goes with, just by the way, x. And then the outputs or the range end up being related to y. So that's another kind of relation, not in the sense that we've got here. It's another way we can kind of define these things. Is domain is the x values that our graph or our equation has, and the range would be the y values that we have. So if we have a graph, then we are able to use what's called the vertical line test to tell if it's a function. And so actually, I guess I haven't really talked about how to do it without a graph either, but let's think about if it's a graph and we want to know, does every x have a unique y? What that ends up looking like is that if I look at this circle and I say, okay, what is if I use 2 as an input right here, if I use 2 as an input, then the output for this circle is the places along x equals 2 along a vertical line that are on this graph. So my output would be these 2 points. That's what we're talking about when we say we want it to only have one output. This is two outputs. When you input 2 as an x value into this circle, you get out an answer that has a positive version and a negative version. So this is not a function. And one of the ways we can do that is we can actually simplify it and say, if I draw a vertical line, which this is going to be a really high quality vertical line. If I draw a vertical line anywhere on the graph, it can only go through one time if it's a function. So here at this particular spot, I drew my vertical line. It went through twice. So you may be thinking, well, there is a place that I could draw a vertical line where it only hits once, right? Either on the left side or the right side of this circle. But what matters is that we have to be able to draw the vertical line anywhere, and it will only ever go through once. So if there's any place that it fails the vertical line test by going through 2 places, then it fails the vertical line test and it's not a function. If you look at, so that's a circle. If I look at the second one, you may or may not know this is a sine wave. So it's the sine that we've been using for trigonometry, SINE, that sign. This is what it looks like if you just graph y equals sine x. And we're going to do some graphing of that in a lesson not too far from now, I don't think. But this sine wave is interesting. If I draw a vertical line anywhere on it, it will only ever go through once. And you can also use your pencil to help you. If you put your pencil, that way you can kind of like move it back and forth and think about it. Like anywhere I place my pencil on this, the graph would only ever go through one time. So this is a function. It's important that we remember that it's the vertical line test, right? So up and down, because if we used a horizontal line on this sine wave, that would not work. A horizontal line, it would go through multiple times. So if there is a horizontal line test, which there is, but we're not going to talk about right now, it would fail the horizontal line test. But it passes the vertical line test, which means it's a function, and that's what we care about. For domain and range, just kind of a by the way, we are going to be using interval notation, which if you've been doing Math UC, I have no idea if it comes up before this or not. I apologize for my lack of information. But interval notation is a way that we talk about things being in between 2 numbers. So for instance, the domain for this circle is that it has x values over to -3 and over to +3. All of our x values are between there. Never on this circle is there an x value of 4 because that's outside of the domain. So the way we'd write this, that the domain is from -3 to 3, is we actually make it look like a point. We put a comma in between -3 and 3, and then we surround it either with parentheses or brackets, but which one we choose is important. We use parentheses when we want to say that it gets close to -3 and 3 but doesn't touch -3 and 3. We'd use brackets if we're saying it does in fact touch -3 and 3. In the case of this circle, the circle actually is going through -3 and 3, so we'd put brackets around this. This is kind of like with inequalities, how we have equal to and not equal to as an option. Actually, it's exactly like that. So this is saying that the domain for this is between -3 and 3, and it actually touches -3 and 3. The range for this, so if I'm looking at my y values, I'm looking up and down. I'm saying, okay, what y values can exist for this circle? It actually has the same range. It goes all the way down to -3 for y. It goes all the way up to +3 for y. And so we'd write -3, 3 with brackets as well. I wanted to go over domain and range because before we actually do the examples on them, because this is something that can be really tricky to understand. So it's my hope that the more we see it, the easier it will be to kind of grasp what's going on here. Let's look at the sine curve and do domain and range on it. So for our domain, because this is going to keep going forever both directions, even though it didn't have arrows, I just added arrows. We know it goes on forever each direction because they didn't tell us otherwise, because it went all the way to the edge of the graph. So those are the kind of things that let us know that, hey, they mean for this to keep going. If it isn't supposed to keep going both directions, then we should see like an actual like point, an endpoint on either side or both sides that is indicating to us that, hey, this is where it stops. So our domain, it goes to the left forever, it goes to the right forever. The way we write that domain, since it can be anything, is we write that as -infinity, +infinity. And we put parentheses around infinity and -infinity because that's just the way we do it. The way I remember is I say, well, you can't be equal to infinity or negative infinity because it's just an idea. You can't actually say, oh, this equals infinity. It equals a really big number, right? So you just always put parentheses around negative infinity and infinity. That's the accepted way of writing it. The range for this one is that even though it goes left and right forever, it actually does not ever end up being above 1 or below -1. It does touch 1 and -1, but it always just keeps going back and forth between those. So that would be -1, comma 1 with brackets. Okay, so we're going to look at some examples using points, equations, and graphs, and it's going to be a really great time. Check it out. Here we've got a couple sets of ordered pairs. Now the squiggly brackets that are around this is a math way of saying, hey, this is a list of numbers. The other word we use in math specifically is we call it a set of things. So we're saying that we have a relation here that is this list of points. It's a completely made up list of points. I made it up in order to do this example. We're supposed to tell whether this relation is a function or not, and if it is a function, they want us to state the domain and range. Now, you can actually still state domain and range if it's not a function. It's just something that we don't do as much, and I don't really know why. That's a pretty standard thing, actually, for instructions on book and textbooks and things, to make you do it for the functions and not for the not functions. So we'll take it, because that's less we have to do if it's not a function. So the way we figure out specifically for a set of ordered pairs, whether this is a function or not, is every x needs to have exactly one answer for y. So as I look at my x values here, okay, 2 has an answer, 3 has an answer, 4 has an answer, 5 has an answer, 6 has an answer. They each have one answer. So this is a function. Now, you may be thinking, well, then what's the opposite? What would it look like for it not to be a function? Let's look at b, and then we'll go back and do the domain and range. On b, -1 has an answer of 5, 1 has an answer of 7, 3 has an answer of -3, 1 has an answer of -9, and 0 has an answer of 5. But wait, how can 1 have an answer of 7 and 1 have an answer of -9? Well, I mean, there's actually ways that could happen, but that means it's not a function because 1 actually has 2 different answers that we can get, 2 different outputs we can get. That means this is not a function. So the takeaway here is that in order to figure out if something is a function, when you have ordered pairs, you need the x's to all be unique. It actually seems backwards because the definition, right, is each input should have a unique output. But when I look at this, I'm looking for the x's being different. The inputs need to be different because if we have a repeated input, that means we probably have 2 answers for that input. They could try to trick us by giving us like 1, 7 and then 1, 7 again. That's technically fine. They've just repeated the same answer twice, but they haven't given us 2 unique answers. So it's kind of weird. All right, we need the domain and range on A. So in this case, we can't use interval notation because these are just random points and they're not connected. Nothing is telling us to connect these points, even if because we love doing like connect the dots, we probably would want to connect these dots. They even make a line. It's like, man, I really want to connect these dots. But we're not going to because we just want to say, okay, the domain is the x values and the range is the y values. So we're basically splitting up the x and y values. And we're going to use squiggly brackets around it. I know those are hard to make. Believe me, I know. So just do your best to make squiggly brackets. Because we want to make a list of the x's and a list of the y's, and the squiggly bracket lets somebody know that what we have here is a list. So 2, 3, I'm just writing down the x values from each point, 4, 5, and 6. You may be thinking, well, couldn't I write that it's between 2 and 6? Well, but it's actually only the integers or whole numbers between 2 and 6. So if you wrote 2, 6 in interval notation, you're saying it could also be 2.5 and 3.5, and that hasn't actually been defined by our ordered pairs. Our range here is the y values, so 1, 4, 7, 10, and 13. Squiggly brackets. Again, the more you do squiggly brackets, the easier they will be to do. So, like, not all of mine are going to look good. Not all of yours are going to look good, probably. And that's okay. We can accept that about each other's squiggly brackets. It's fine. Let's look at example 2. Tell whether each of the following relations is a function. If the relation is a function, state the domain and range. So same instructions, but now we have 2 equations. And in the MathUC workbook, on the ones with equations, they then have like a place that I think they want you to make a list of points that goes with the equation, because I think they're trying to get you to kind of relate the two, situations. And that's fine. We could do that. We could say, okay, well, if I pick something for X, what do I get for Y? We could make a list of ordered pairs, and hopefully then we'd come up with the idea that, well, either this is or isn't a function as we're going through that process. Because really, in order to figure out based on an equation what's happening, you need to either look at the graph or think about the points or have in your head just some knowledge about what this is. Now, we haven't graphed things like this year in MathUC Precalculus, so it may take you a second to remember, but y equals 2x plus 3 is a line in slope-intercept form. And since it's just a diagonal line, if we think about the vertical line test, we actually can come up that way with whether or not it's a function. So that's one way, is you can look at the graph, use the vertical line test. And since we all have calculators, or we probably have calculators, and if we don't have calculators, we can use Desmos, D-E-S-M-O-S, which is a free online graphing calculator that is amazing, but that does not pay me to say that. Hint, hint, wink, wink, Desmos, although I don't know how they make money, so I don't know how they would pay me. Anyway, if we graph this, we can see, okay, it passes the vertical line test. But the other idea is to say, if I put a number in for X, how many answers am I going to get for Y? Is there a thing that would cause me to get more than one answer for Y? And think about it. If I plug in 1, I get 5. If I plug in 2, I get 7. Like, I keep getting one output every time I input something. That's because it's a function. So however you want to think of it, whether you want to just look at the graph, that's fine. But this is a function. Looking at the graph is the easiest way, though, to find domain and range, because whenever you do it just based on the equation, you're still having to basically picture in your head what this looks like. So if I graph y equals 2x plus 3, I get a diagonal line. It has a slope of 2, so it's actually kind of steeper than this probably, and it goes through 3. But for domain and range, the important thing here is that it goes forever left and right, and it goes forever up and down, and nothing stops it from doing either of those. There's no random curve or like just thing that, like, there's not a wall that stops it. I don't know why we'd have a wall on a line anyway. So the domain for this is negative infinity, comma, positive infinity. And the range for this is negative infinity, comma, positive infinity. And again, it's just standard practice to put parentheses around negative infinity and infinity. You could argue with me if you wanted to that brackets make sense because it touches infinity and negative infinity because it goes on forever. You could do that, but I'm not in control of this. I'll be like, yeah, I totally get it, but that's not how we have decided to do it. You could grow up and try to change that if you wanted to, and that I'd be all on board with that. Let me know. But in the meantime, there's parentheses around it because we're not equal to infinity or negative infinity. Now, x equals 5 is a little trickier. If you try to graph this on your TI calculator, you may notice you can't because your graph says, your graphing thing says y equals and this is x equals, and there's not a way to change that. That actually is part of the issue that helps us know that this is not going to be a function. Spoiler alert. The other way is to, on Desmos, it will graph this, by the way. So if you graph x equals 5, it'll help you remember that, hey, this is a vertical line that goes through 5. The other thing that we could think of is if we're making a list of points, our x would have to be 5 because x equals 5. Well, it would have to be 5 the whole time we're making our list of points. So this could be whatever we want it to be, but the input has to stay the same because it's saying, no, x equals 5. It doesn't equal anything else. It just equals 5. So we've got a repeated x value. That's a way to say, hey, this is not a function. The vertical line test, it fails because it is a vertical line. If you put a vertical line on top of a vertical line, then it's going to intersect infinitely many times. It's going to intersect all the time. So however you want to think of it, this is not a function. I do feel like I should give you a hint here, like lines in general, other than vertical lines, will be functions. And probably the other things that we've graphed, I would assume up until now, maybe not. Maybe you've encountered some not functions in algebra too. But most of the things that we've graphed up until now are functions. Parabolas are functions. So you should have before now graphed parabolas. In general, they are of the form y equals x squared. If you put something into x, you square it and you get an output, and it's great. And so you may actually be thinking, well, like, what would an equation look like that would give me something that's not a function? And basically, it's whenever we square y instead of x. So you may have done this in algebra 2, you may not have. If you do x equals y squared instead of y equals x squared, you end up with a parabola on its side. And so that fails the vertical line test. So seeing y squared is a big red flag that this is not a function. The circle we had earlier, that equation would have been x squared plus y squared equals 9. So you see again, we have a y squared. The other thing I can think of would be we could have x. Basically, your key thing is it being solved for x instead of for y. It's not necessarily it doesn't necessarily mean it's not that it is a function. Wait, it doesn't necessarily mean it's not a function if it's solved for x. But if it's solved for x and you're a little unsure of how to solve it for y, that's a big red flag that it might not be a function. So having absolute value bars around y would be an issue because that gives us, at least I think this is right, that gives us a absolute value graph on its side. I guess I could ask Desmos because I have it on my other monitor. Yeah. I'll just drag this over. See, y equals absolute value of y is a v, but on its side. So it looks like a greater than symbol. No, a less than symbol. I'm good at this. So I just wanted to throw out there because I would imagine if you're like, okay, well, I get that the vertical line isn't a function, but when else would we not have a function? Because so many of the things we encounter in math are functions because we like functions. Like that's really the thing. I'm not actually entirely sure why we like functions so much, other than they start with the word fun, but we do. So there we go. Let's look at example 3. We've got some graphs here, and I copied the instructions from the workbook that said answer the questions for each drawing. If the drawing is not a function, write NA after the questions about domain and range. But then I didn't actually write down the questions. It asks you on each graph, is this a function? What is the domain and what is the range? So now we know. So if we have a graph, we should use the vertical line test. So A is just some points, they're not connected. But if you imagine putting a vertical line on any of these points, it only goes through a single point. So it is a function. So it'd say, yes, it's a function. And then because we want the domain and range, and this is points, we're gonna use squiggly brackets. Each of our points, we're gonna break up into its x's and y's. So you may actually wanna sit here real quick and go, okay, this is -1, 0. This is 0, 2. This is 2, 3. This is 1, 4. And typically when we're writing things as a list, we usually write them from least to greatest or most negative to most positive. I don't know that there is actually an official rule that says you have to do that, but it's considered like best practice or nicest. So our points have x values of -1, 0, 1, and 2. And our y values have 0, 2, 3, and 4. So for B, is this a function? Think about a vertical line. Anywhere we put it, it only goes through this line one time. So this is a function. Now for our domain and range, this is one of the ways that we might have a situation where, okay, this is stopping. There's no arrows on the end. In fact, there's a point at each end trying to signify for us, right, that this is stopping. So how far does this go to the left? It stops here at -3 and doesn't go past -3. It stops at 2 on the right and doesn't go past 2. It does touch both of those. The way it would tell us that it doesn't touch, the thing that would make us say, oh, I need to put parentheses, would be them putting an open circle, which should make you think back to linear inequalities. That would have told us that it didn't touch. Or we have these things called asymptotes, where like our graph might curve up and then just look like it goes vertical. And so it like never actually touches whatever this point is. And so that's another time where we would use parentheses. I'm going to erase that because I got in the way of my range. But that doesn't happen here. So we're from between -3 and 2 with brackets. And then for range, we're from -1 to 4 with brackets. For C, vertical line test, this fails because if I put a vertical line down anywhere other than the far left, right, it ends up going through twice. And it just matters that at some point it does not end up, it matters that at some point it fails the vertical line test. If it fails anywhere, it fails the whole thing. I know that seems like a really unfair test. We would not appreciate having a test like that probably, but it's math, so it's fine. And then we don't have to put the domain and range since it's not a function. We could, but we don't have to. Thank you so much for watching. I hope you enjoyed this. Please subscribe and like. Subscribe if you haven't already. Like whether you have already, well, don't like it if you've already liked it, because I think then you wouldn't have liked it. Anyway, I'll see you in the next video. Thanks.